A very good morning to all. Welcome to another session on remote sensing and GIS. In this class, we are going to see unit number three's second part. Unit number 3 deals with optical and microwave access, which is used for remote sensing in today's applications. So let us proceed on to the today's presentation on unit number 3. Unit 3 optical and microwave access, which is used in remote sensing. So let us move on to the topic called scanners. So in previous class we had seen optical access, satellite access, LEO, MEO, GEO, HEO that are being used in orbiting of satellites in space. Following the optical and microwave access for remote sensing, we need to see a specific type of device or an equipment that is used for data acquisition. So that we call it as a remote sensing scanner. Now to have a global coverage, we place our satellites in the space depending upon the application. Either we place it in low Earth orbiting, or in medium Earth orbiting, or in high Earth orbiting, or in geosynchronous orbiting. So depending upon the application, the equipment being used for data acquisition will also vary. So generally, these equipments that are used for data acquisition used is your scanner. Okay. So since it is specifically used for remote sensing, we call it as remote sensing scanners. So scanner is a device for examining, reading, or monitoring something in particular. You can see an example: a satellite is there, an application. A satellite is present; it is revolving around the Earth, where the Earth is rotating in its own axis. You can see a scanner is also moving, and it is monitoring the same region. You can see. And see here, you can see in the second image at the bottom, you have a scanner which is being placed in this place, which is used just tracking like this. You can see the scanner is tracking this part as well as this part. Okay. A device that scans documents and converts them into original data into digitally. We call it as a scanner. So there are many electronic remote sensing systems that use scanners which employ or which has a sensor with a narrow field of view that sweeps over the terrain to build up and produce a two-dimensional image of the surface. So these scanning systems can be used either in aircrafts or in satellite platforms having the same operating principles. So either by using an aircraft, you can get the data acquisition or by using a satellites. So in this case, a multi-band imaging system is being deployed to sense the Earth's field by using the energies that are being reflected in multiple wavelength bands. So that we call it as multispectral band or multi-band imaging technique. So there are different types of scanners being used. One of them is the multispectral scanner, which I just now said. Okay, multi-band imaging. A type of that is your multispectral scanner. A scanning system that is used to collect data over a variety of wavelength ranges is called as multispectral scanner. So over a electromagnetic bandwidth, we can use this multispectral scanner to detect all the variety of different wavelengths, such that all the scanning can be done with a single equipment. So this multispectral scanner operates in spectral bands which is in the range of 0.3 to 14 micrometers. The multispectral scanner uses a sensors that are present in line observing the Earth perpendicular to the orbital track. Along the orbital tracking, these scanners will be in linely placed, the sensors. So the cross-track scanning will be accompanied by an oscillating mirror. There will be 6 lines being scanned simultaneously in each of the 4 spectral bands for each mirror sweep. The forward motion of the satellite provided the along track scan line progression. This multispectral scanner system that acquires data in both visible and infrared wavelengths will have an oscillating mirror to scan the Earth behind the spacecraft. There are some terminologies to be learned which was being deployed in the Landsats that carry this multispectral scanner system sensors. So the first 5 Landsats carried the MSS sensor which responded to Earth reflection sunlight in 4 spectral bands. So those 4 spectral bands are 0.5 to 0.6, 0.6 to 0.7, 0.7 to 0.8, 0.8 to 1.1 micrometers. In these bands, they use the sensors. Whereas in Landsat 3, this carried an MSS sensor with additional bands, designated band 8, that gave enormous response to the thermal infrared radiation. Similarly, an IRS, Indian Remote Sensing, LISS 3 sensors operated in 4 bands, 0.52 to 0.59, 0.62 to 0.68, 0.772, 0.86, 1.55 to 1.70 micrometers. In the first 3 in the visible region and near infrared region, and 1 in the middle infrared region of the electromagnetic spectrum. So like this, IRS, Indian Remote Sensing satellite sensors were being used. So another feature of the spectral is that the spectral reflectance of the features that differs in different wavelength bands. So the features are identified from the image by comparing the responses over different distinct spectral bands. So the broadly classified systems for them are your water, vegetation that we had seen in the previous classes, how water, which region water has the highest reflectance curve in dry vegetation and wet vegetation, how is the spectral reflectance characteristics and all, which were used at different wavelengths. So these informations were being recorded by the spectral reflectance. So for this, there are two main modes or methods being deployed to acquire the multispectral image data. The first one is the across tracking scanning, and second is the along track scanning. These two methods are being deployed for scanning such that the scanner sensor will acquire data appropriately depending upon the need and application. So two modes, across track and along track. This is an example of MSS scanning arrangement. We have a detector segment. 6 detectors are used per band. So totally 24 for 4 bands. For every band we'll be having 6 detectors. So since there are 4 bands, we have 24. So these are being placed here. So then we have a pillar, okay, which will acquire the data. Then we have the oscillating scan mirror. So this oscillating scan mirror will be focused towards the earth, in which direction we want to scan. So there will be 6 scan lines. So these 6 scan lines is your resemblance of your 6 detectors per band. So the field of view FOV, which you had seen, should be 12 degree with a swath width of 115 miles. So as the sensor moves with respect to the satellite, so this will capture images, which is the direction of orbital flight in this direction. So it will capture as it is, and that will be recorded in your system and being sent to your processing segment. So MSS scanning arrangement. So this will be repeated for every other bands also. Same procedure. So this is a simple multispectral scanner system which uses energy energy which is being drawn from the ground surface that falls on the oscillating mirror. So that oscillating mirror is focused towards the optics. So that optics sends the captured signal into a diachronic grating. So that diachronic grating is given to the sensor or the detector, so which will convert the information through an electronics part, and then it is being recorded by tape recorder or a device. So this is the multispectral scanner system diagram, how it works. So depending upon the wavelength which is being operated for the 4 bands, it will be split up for 6 detectors. So there are many electronic remote sensors that acquire data using scanning systems that employ a sensor with a narrow field of view or IFOV that sweeps over the terrain to build up and produce a two-dimensional image of the surface. These scanning systems can be used on aircraft as well as satellite as said already with the same operating principles. The scanning system that is used to collect data over a variety of different wavelength ranges is called as MSS, multispectral scanner. And this is the most commonly used scanning system in remote sensing. And the two different types, across track and along track, we'll see that. So this is the example or the diagram of your across track. It scans the earth in a series of lines. As you can see, lines are being put up. Okay, the lines are perpendicular to the direction of motion of the sensor platform. You can see the lines are perpendicular to the direction of motion of the sensor platform. So this is your sensor platform which is moving. So it is perpendicular to that. So that is across the swath. So that is the reason why we call this as across track scanner. So each line is scanned from one side of the sensor to the other using a rotating mirror. You have a rotating mirror here that rotates, and depending upon the rotation, this scanner will scan each and every line from one side to the other till the focus. As the platform moves forward over the earth, as the platform, so this aircraft platform or the satellite platform which moves over the surface of the earth, successive swath scans. So means that first line will be scanned first, then the second line, then the third line, then the fourth line, then fifth line. After successive scans, we'll get an two-dimensional image of the earth surface that you can see in the bottom diagram. You can see. So this scanning is done with respect to the instantaneous field of view. The first line, second line, third line, fourth line, fifth line, sixth line, it goes. So that information is being recorded and it is being built up as a two-dimensional image of the earth surface across track scanners. So then we have a bank of internal detectors as said earlier, which is B. You can see here B. This is B. Where these detectors are sensitive uh, sensitive to a specific range of wavelength, detects and measures the energy for each spectral band. The incoming energy is separated into several spectral components that are independently sensed. The incoming energy is separated into several spectral components that are independently sensed. Because the distance from the sensor and the target increase towards the edges of the SWAT, the ground resolution cells also become larger, and then they introduce a geometric distortion to the images. So this is what happens in across track scanners. So any queries about this across track scanners, you can type in chat box. Then I'll proceed for the next scanner, which is along track. Okay, thank you, Sai Ganesh. Since there are no doubts, we proceed further on to the next topic, which is your along track analysis. Okay. So the same image going to show how the across-track scanner works. So A is your rotating mirror, B is your recorder, D is your object that you are scanning, and C is the path, which is IFOV. So the procedure is this. Across-track scanner scans the Earth in a series of lines. The lines are oriented perpendicular to the direction of motion of the sensor platform. Each line is scanned from one side of the sensor to the other using a rotating mirror A. As the platform moves forward over the Earth, successive scans build up a two-dimensional image of the Earth's surface. The incoming reflected or emitted radiation is separated into several components that are detected independently. Mostly, the ultraviolet, visible, near infrared, and thermal radiation are dispersed into their constituent wavelengths. Then we have a bank of internal detectors B that are sensitive to a specific range of wavelengths, detecting and measuring the energy for which the spectral band as an electrical signal, and then they are converted to digital data and recorded for subsequent computer processing. Then we have the IFOV of the sensor and the altitude of the platform that determines the ground resolution cell view, which is D. And thus we get the spatial resolution of that. Then we have the angular field of view, that is a sweep of the mirror measured in degrees. And also it records the scan line, thus determining the width of the sorry for the interruption. The angular field of view IFOV is a sweep of the mirror that is measured in degrees, which records a scan line and determines the width of the imaged swath, which is your F. We have an airborne scanners that typically sweep large angles between 90 and 120 degree. While the satellites, due to their higher altitude, need only to sweep fairly a small angle covering of 10 to 20 degree to cover a broader region. Since the distance from the sensor to the target increases towards the edges of the swath, the ground resolution cells also become larger and introduces geometric distortions, as already said. Also, the length of the time The IFOV sees a ground resolution cell as the rotating mirror scans is called as a dwell time. Keep in remembrance the definition of the dwell time, which is an which plays an important factor in the scanning of your images, which is generally a quite short and influences the design of your spatial, spectral, and radiometric resolution of the sensor. Next is the along track scanners. The difference is between the across track and along track is that instead of using a scanning mirror, we use directly a linear array of detectors which focuses on the track. Okay. So this linear array of detectors locates the focal plane of the image formed by the lens systems which are pushed along the flight track direction. So A, B, C, D. D is the object that is to be scanned. You can see inside the sensor directly we have an CCD arrays, charge coupled device arrays, that are used to scan the D part, as you can see this D part easily. Rather than using mirrors, we'll be using linear array of detectors. Prominently CCDs are being deployed for this purpose. Each individual detector will measure the energy for a single ground resolution of the D. Thus, the size and IFOV of the detectors will determine the spatial resolution of the system. So, a separate linear array is required to measure each spectral band or channel. So, you can see inside the sensor we have a CCD array, a platform or a sensor which is being present, which tracks along the scan direction, and this is the flight direction as it goes. This is a more explanatory diagram where A is your linear array of detectors, B is the plane of the image formed by the lens C, then D is the object that we are determining. So along track trackers use the forward motion of the platform to record successive scan lines and builds up a 2D image perpendicular to the flight direction. Whereas across track also does perpendicular to the flight direction. Difference is using an array. Instead of using an scanning mirror, here we use an linear array of detectors located at the focal plane of image B, formed by the lens system C, that are pushed along in the flight track direction. As the flight moves, in which direction, in that direction it will be taking. So that is the along track. Along the flight, it moves. Then we have the push broom scanners. So this are also called as also referred to as push broom scanners, as the motion of the detector array is analogous to the bristles of a broom being pushed along a floor. So each individual detector measures the energy for a single ground resolution cell D, and thus the size and IFOV of the detectors determines the spatial resolution of the system. A separate linear array is required to measure each spectral band or channel. For each scan line, the energy detected by each detector of each linear array is sampled electronically and digitally recorded in tape recorders. Example of whisk broom and push broom scanners, depending upon the application. Diagram A is your whisk broom, diagram B is your push broom. These two images will give you the Difference of both cross-track, across-track, and along-track scanners. So the scanning rate is 2 into 10 power minus 2 seconds per scan line for across-track. So the number of cells per line will be 2000 cells. For every line, we will have 2000 cells. So with that, we can find the dwell time in across track. So the scan rate per line divided by number of cells per minus 2 seconds divided by 2000 cells. Since every line has 2000 cells, so dwell time will become 1 into 10 power minus 5 seconds per cell. For every cell, the dwell time is 1 into 10 power minus 5 seconds in whisk broom or the across track scanner. Or approximately, we can write it as 0.1 microseconds is the dwell time. Then, if you see for alarm track scanner, the dwell time can be measured by the cell dimension divided by velocity. So the cell dimension is 10 meter per cell. For every cells, 10 meters. And depending upon the velocity of the platform, whether the aircraft platform or the satellite platform that it moves on. So it is that is to be considered. So 10 meters divided by 200 meters. If you take the ratio between the cell dimension and velocity, we'll get the dwell time of the alarm track scanner, which is per 10 by 10 meters. With the velocity of 200 meters, we'll get 5 to 10 power minus 2 seconds, which is 0.5 milliseconds per cell. So depending upon the requirement and need, we can use which system or which scanner is to be decided by the designers. The advantages of alarm track scanners. This measures the energy from ground resolution cell for a longer period of time. More energy can be detected and improves the radiometric resolution. The smaller IFOVs and narrower bandwidths for each detector. The cross calibrating is being done for thousands of detectors to achieve uniform sensitivity across the array. Is a major advantage of the alarm track. Next topic is thermal imaging. Thermal imaging is an important concept where it uses infrared region of the electromagnetic spectrum, which detects the Earth's thermal images very efficiently and says what type of property that object or the target is. For this, the multispectral sensor systems sense radiation in the thermal infrared as well as the visible and reflected infrared portions of the spectrum. However, the remote sensing of energy emitted from the Earth's surface in thermal infrared, which is approximately 3 micrometers to 15 micrometers, is different than the sensing of the reflected energy. So for this, thermal sensors use photodetectors that are sensitive to the direct contact of photons. that fall on the surface and detect emitted thermal radiation. The detectors are cooled to temperatures close to absolute temperature in order to limit their own thermal emissions. So this cooling is a major disadvantage of the thermal imaging, whereas it produces higher efficiency in retrieving the objects on the Earth. The thermal scanners essentially measure the surface temperature and thermal properties of the targets. So this is an example of that. A detector is there that senses the data through the lens, and what it detects is that is present on the Earth's surface. So all the radiations are being absorbed by the lens, and depending upon the detector, it transfers the information to the electronics and then to the image or data, which is recorded there. Thermal images are typically across track scanners that detect emitted radiation only in the thermal portion of the spectrum. So it uses across track scanning principle. These thermal scanners employ one or more internal temperature references for comparison with the detected radiation. So they can be related to absolute radiant temperature. The data are generally recorded on film and or on magnetic tapes, and the temperature resolution of current sensors can reach 0.1 degree Celsius. So this is an image of radiant temperatures done by a thermogram. Depending upon the temperature of the Earth's surface or the object, we can find what object or what it is. You can see relative radiant temperatures is deposited in gray levels, with warmer temperature showing in light tones and cooler temperature showing in dark tones. So you can see that these dark tones has temperature is that it is very cool in these places. So in these places where we have light light tones or brightish colors, here there is warmer temperature or high temperature. So with this we can find how much temperature is present, or how much temperature does that object radiates. So another example of this thermogram is what you see in nowadays in crickets. In cricket, a thermo image will be shown where the ball passes through the batsman during an DRS system, decision review system, where they take it, the ball, whether it touches the bat, pad, or any other objects, if there is a DRS being reviewed for LBWs or caught behind or whatever might be. So this imagery which portrays relative temperature differences in the relative spatial locations are sufficient for most applications. Absolute temperature measurements may be calculated that require accurate calibration and measurement of temperature references depending upon the thermal properties of the target, geometric distortions, and radiometric effects. Because of the relatively long wavelength of thermal radiation, atmospheric scattering is minimized. However, absorption by atmospheric gases normally restricts thermal sensing to two specific regions, which are 3 to 5 micrometers and 8 to 14 micrometers. Since energy decreases as the wavelength increases, thermal scanners generally have larger IFOVs to ensure that sufficient energy reaches the detector in order to make reliable measurements. Therefore, the spatial resolution of thermal sensor is usually fair relative to the spatial resolution possible in the visible and reflected infrared region. The thermal imagery can be acquired during the day or night and is used for a variety of applications such as military, reconnaissance, disaster management, and heat loss monitoring. So this is an example of the thermal scanner. It is thematic mapper. So before starting the thematic mapper, any queries, type in chat box. Since I couldn't find any queries in the chat box, I further move on to the thematic mapper. The thematic mapper is an advanced multispectral scanner which is designed to achieve high spectral, spatial, and radiometric accuracies. This was introduced by the NASA during the Landsat 4 mission. So this Landsat mission was operating on a 7-band structure. 7 bands were being used rather than the 4 bands in earlier. So this sunbands provided a 30-meter spatial resolution. So this thematic mapper is an example of a whisk broom scanner that will take multi-spectral images across its ground to collect data with more wavelength bands. So this does not directly produce a thematic map. These bands are more refined compared to the multispectral scanner system and are designed for some potential applications. So let us see the device of the thematic mapper. You can see this is your thematic mapper device. This is your scanner. It is focused towards the earth side. So if this thematic mapper is being used, how it takes images, you can see here. So the thematic map is shown here. So these are the photographs taken by the thematic mapper resolutions. Where it has been divided into 7 bands. One is the blue band, green band, red band, near infrared, short wave infrared in 2 different regions, and thermal infrared, which is divided into 0.45 to 0.52 for blue, 0.52 to 0.6 for green, 0.63 to 0.69 for red, 0.76 to 0.90 to near infrared, 1.55 to 1.75 for short wave infrared 1, and 2.08 to 2.35 for short wave infrared 2, and 10.4 to 12.5 micrometers. Everything in micrometers for thermal infrared. You can see an thematic mappers picture. It is taken in false color infrared, near infrared, red and green. So the corresponding wavelengths will be reflected. These pictures were being taken by the Landsat TM5. So the potential applications of the TM5 is being shown here. Landsat TM5, spectral bands and their applications. The band 1 having spectral range from 0.45 to 0.52 is used for water mapping, soil vegetation differentiation, and deciduous coniferous differentiation, which is blue color. Then 0.5 to 0.6 micrometers. The principal application is used for grain reflectance by healthy vegetation. Whether it is good vegetation or dry vegetation is being determined by this spectral band. The spectral band 3 having spectral range 0.63 to 0.69 micrometer is used for chlorophyll absorption or plant species differentiation applications. Fourth one is the Fourth spectral band is the 0.76 to 0.90 micrometer, which is used for biomass surveying, water body delineation application. Next band is the band 5, where the spectral range is from 1.55 micrometer to 1.72 micrometer, which is used for vegetation, moisture measurements, snowfall, or snow cloud differentiation. For that application, it is being used. The spectral band 6, having ranges from 10.4 to 12.5 micrometers, is used for plant heat stress measurement application and other thermal mapping measurements. The band 7 spectral band in this range of 2.08 micrometer to 2.35 micrometers used for hydrothermal mapping application. So depending upon the need and application, this Landsat was being done. Landsat thematic mapper. Next is the in the circular scanner. The scan motor and mirror are mounted on a vertical axis of rotational that sweeps circular path on the terrain. You can see a scan mirror, a motor that rotates, and this will take in circular path such that it will be detected. Only the forward portion of the sweep is recorded to produce images. The circular scanners are used for reconnaissance purposes in aircrafts. These images are displayed in real time on a screen in the cockpit to guide the pilot such that they move the aircraft in an appropriate position. Next type of scanner is your thermal scanner. This is a special type of across-track multispectral scanner which senses the energy and thermal wavelength in the range of electromagnetic wave spectrum, ranging in 4 different regions, as we had seen in the earlier slides. And the thermal scanners was being developed by, yeah, NASA JPL, Jet Propulsion Laboratories, and the Daldas Corporations. They developed the advanced spaceborne thermal emission and reflection radiometer, which is called as ASTER. They had put it on board in Terra, which is used for thermal infrared multispectral scanning. Okay, TIMS. So this ASTER data is used to create detailed maps of land surface temperature, reflectance, and elevation. So this thermal infrared multispectral scanner is used as an airborne geologic remote sensing tool to acquire mineral signatures to discriminate minerals like silicate, carbonate. So this uses a six wavelength band channels. So this six bands of the TIMS, which is your thermal infrared multispectral scanner, is being shown here. The channel 1 is given for 8.2 to 8.6 micrometers, channel 2 8.6 to 9 micrometers, channel 3 9 to 9.4 micrometers, channel 4 9.4 to 10.2 micrometers, channel 5 10.2 to 11.2 micrometers, channel 6 11.2 to 12.2 micrometers. Since the energy received at the sensor decreases as the wavelength increases, the larger IFOVs are generally used in thermal scanners to ensure that enough energy reaches the detector for reliable measurements. Therefore, the spatial resolution of thermal sensors is usually fairly close related to the spatial resolution that is possible in the visible and reflected infrareds. However, due to the relatively longer wavelength, atmospheric scattering is minimal in thermal scanning. Also, since the reflected solar radiation is not measured in thermal scanning, it can be operated in both day and night times. Most of the important applications of thermal remote sensing images are as follows. The geological studies, which determines the type of rocks, structures of rocks, and then this thermal remote sensing is used in soil mapping, to find soil moisture studies, study of evapotranspiration in vegetation, detection of heat losses in buildings, detection of damages of steam line pipes and caliducts, detection of subsurface fires due to forest firing or coal firing in some factories. For all this purpose, thermal remote sensing can be used. Next type of sensor, we have the imaging spectrometers. For this, we use an high spectral sensor that acts as the instruments for acquiring images in several narrow and contiguous spectral bands in the visible, near infrared, middle infrared, and thermal infrared regions of the electromagnetic spectrum. These hyperspectral sensors could be along track or across track. So a typical hyperspectral scanner will record more than 100 bands, and thus it enables the construction of a continuous reflectance spectrum for each pixel. For example, a Hyperion sensor on board in NASA's EVO-1 satellite. The Earth's surface is having a contiguous spectral bands of 220, covering the region from 400 nanometer to 2.5 micrometer at ground resolution of 30 meter. IRS sensor, which is developed by the JPL, will have 4 spectrometers with a total of 224 individual CCD sensors or channels, each with a spectral resolution of 10 nanometers and a spatial resolution of 20 meters. So this is the hyperspectral sensor. Here, this is an example of an hyperspectral sensor. This is a perception of a human eye, which is equivalent to a hypersensor, high spectral sensor. So this is your lithographed image. The spectral dimension in those bands, those are being converted into hyperspectral cube in the dimension of two dimensionals, which is being convolved on a spectral signature varying from 0.4 to 2.5 micrometer wavelength. So this is the device, how it looks, a pictorial representation of that. From the data acquired in multiple continuous bands, the spectral curve for any pixel can be calculated that may correspond to an extended ground feature. Hyperspectral sensors look at objects using a vast portion of the electromagnetic spectrum, where certain objects leave unique fingerprints in the electromagnetic spectrum known as spectral signatures. The hyperspectral imaging has wide-ranging applications in remote sensing applications of mining, geology, forestry, agriculture, and environmental management. So this system enables discrimination of iron oxides in soil, clays, carbonates, weathering products from sulfides, and many more. Always the natural color image data is comprised of red, green, and blue. The color infrared data is comprised of infrared, red and green bands. For multispectral data containing more than 3 spectral bands, the user must choose a subset of 3 bands to display at any given time. The multispectral imagery generally refers to 3 to 10 bands that are representing pixels, where each band is acquired using a remote sensing radiometer. So these are the examples of multispectral system sensors, scanner sensors. So these are used in Landsat multispectral scanner, Landsat thematic mapper, NOAA, advanced very high resolution radiometers, AVHRR, NASA, and OrbImage. It is used in Daedalus aircraft multispectral scanner, NASA airborne terrestrial application sensor, Atlas. Then the multispectral imaging using linear arrays are used in spot 1, 2, 3, high resolution visible HRV sensors, and spot 4 and spot 5 are used in high resolution visible infrared HV, IR, and vegetation sensors. This linear array is used in Indian Remote Sensing System, IRS, Linear Imaging Self-Scanning Sensor, LISS. And it is used in NASA, Terra, ASTER, Advanced Spaceborne Thermal Emission Reflection Radiometer. NASA Terra, MISR, Multi-Angle Imaging Spectroradiometer. using linear and area arrays. NASA Jet Propulsion Laboratory Airborne Visible Infrared Imaging Spectrometer AVIS. Then this is used in Compact Airborne Spectrographer Imager 3, CASI 3. Then this is used in NASA Terra Moderate Resolution Imaging Spectrometer MODIS. It is used in NASA Earth Observer EO1, Advanced Land Imager ALI, Hyperion, and Lycia Atmospheric Corrector LAC. So this is the sketch of an multispectral system providing an open system interface. So how it occurs. So light source, on this the sun's radiation falls, it is being captured by any of these spectrals, 7 spectrals, which we call as a spectral filter wheel. So it filters, so that information is given to the data transmission through multispectral cameras. So these multispectral cameras will acquire this information, and it is given to the encoding of multispectral data, which is this. So then it is being data transmitted to the multi-channel display, where decoding and controlling is done there. Then the multi-channel display and the exact replication of this rose flower is being given here. This is how multispectral system works. So this is an example of multispectral image documentation. Invisible, an image will look like this. In raking light, RAK, it will look like this. In ultraviolet fluorescence, it will look like this. In UV reflected, ultraviolet reflected, it will look like this. In digital infrared, it will look like this. Then if the same image in infrared false color, IR, FC, it will look like this. In infrared fluorescence, it will look like this. In infrared transmitted, it will look like this. In infrared IR reflectography, like this. In back visible, it is like this. And back digital IR, it will look like this. So this is how the multispectral documentation is done for specific images. So the major differences between the multispectral and hyperspectral is shown here. The broadband is being classified into visible, short wave infrared, and long wave infrared. Multispectral is classified into 7 bands. Band 1 in the 0.45 to 0.52 micrometer, band 2 in 0.52 to 0.60 micrometer, band 3 in 0.63 to 0.69 micrometer, Band 4, 0.79 to 0.90 micrometer. Band 5, 1.55 to 1.75 micrometer. Band 7 in 2.08 to 2.35 micrometer. Band 6 in 10.4 to 12.4 micrometer. So whereas in hyperspectral, these are being divided into hundreds of bands. Hundreds of bands. And in ultra spectral, it is being divided into thousands of bands. So that is the major difference in spectrum. It is taken from the electromagnetic spectrum again. So these are the details of that. Spectral bands in terms of nanometers. Now we are classifying, since we need to since we are dividing it into small 100 bands, so we need to write in terms of nanometers, so that will be more easier. So 410 to 515 to 520 nanometers used for atmospheric and deep water imaging, so which can reach up to a depth of 150 feet, which is 50 meter in clear water. Green, 515 to 600 in that range, is used for imaging vegetation and deep water structures up to 90 feet, 30 meter, which is in clear water. Red, 600 to 690 nanometer, is used for imaging man-made objects in water up to 30 feet, which is 9 meter depth, soil and vegetation that can be obtained. So 750 to 900 nanometer is used primarily only for image vegetation. And middle infrared, 1550 to 1750 nanometers, used for imaging vegetation, soil moisture content, and some forest fires. Whereas another region of mid infrared from 2080 to 2350 nanometers, used for imaging soil, moisture, geological features, silicates, clays, and fires. And the thermal infrared from 10,400 to 12,500 nanometers, used for measuring emitted reflections of geological structures, thermal differences in water currents, fires, and is used in night studies. Then we have the radar. So this for mapping terrain and for detecting various objects. So that we'll see radar in the subsequent classes. This is the spectral band usage. It is done in 3 different colors, as you can see. As you can see, it is the true color, which uses only red, green, and blue channels, mapping to their respective colors. Then we have the green, red, infrared band usage, where blue channel is replaced with near infrared and is used for vegetation. Then blue, near infrared, and middle infrared, where the blue channel uses visible blue, green uses near infrared, so vegetation stays green, and middle infrared is shown as red, so which is used for water depth and vegetation coverage. So this is the characteristics of a wireless airborne multispectral across track scanner. So you can see that a airborne multispectral scanner is present, so that is deployed in aircraft. So during motion, it takes the line of flight, it captures the information from the ground, D, which is the object, so it scans line by line, line by line, line by line, and this gives information. What is it has is that it has the scanning system, where the radiant energy or the flux from the earth's surface is captured, through the optics, through the mirror, to the diachronic grating as we had seen. Then it is given to the prism for spectral variations. Then we have the thermal detectors. Then it is those signals that are being recorded according to the information is being given to a system which monitors. So it is which is the monitor power digitizer and data recorder, which is present in the electronic segment. So till this tracker and the scanner, multispectral scanner, I stopped today's session. So any queries, type in the chat box. Yeah, thank you, Sai Ganesh. The remaining topics of Landsat, Spot, IRS, Indian remote sensing, all will be seeing in tomorrow's class.